Hello, I'm Daniel Pulipati, a research scientist at Baylor University, and I've been spending a few years studying about the polymer composite crossties that are used with recycled materials, and I'm here to present on the nonlinear structural analysis and in situ testing of composite railroad ties. So to introduce this topic, most recycled polymers are single-used. You use them, then they're thrown away, and they're either recycled or put in a landfill, or they're incarcerated. Some of the commonly used polymers are low-density polyethylene, high-density polyethylene, and so on. And once they're used, like I mentioned, they go into a lot of waste. So this is some of the wastes that are collected and are ready to be reused. A recent study was done to see how much polymers were recycled, and about 35% of it is polyethylene, and 40% of it is polypropylene, and 20% is polystyrene, and there's some traces of other polymers. If you're able to find solutions for polyethylene and polypropylene, which constitutes about 75 to 85% of all the polymers, that's a huge success. The method that we use is using high-density polyethylene, glass fiber polypropylene, blowing agents, and carbon black. Carbon black is used to add UV stabilization, and the blowing agents for foaming the center of the composite crosstie. They're used using an extrusion molding process, and once the polymer is sent into the mold, it cools down, and as it's cooling down under temperature and pressure, blowing agent enables formation of cells, and you can see over here, the corners and the edges have solid shell region, but the center is foamed with lots of closed cells. This can be used in various applications. Over you can see they can be used for fences, short bridges, some boardwalks, benches, stables, even in parking lots and so on. And some of the major structural applications are the railroad ties, marine pilings, construction mats, and you have short bridges for using high structural loads as well. I will hand over to David Jack for the presentation.
Thank you, Daniel. I do thank you for the opportunity we have here to present Rail Tech. It's a great opportunity to talk about some of the work we've been doing here. I'm going to talk for a few minutes about the methodology overview and some of the mathematical foundations. Again, this is just kind of a taste about the bigger picture. So what we're doing is we're starting with, of course, obviously the large cross tie itself. Well, this cross tie, what we want to do at the end of the day is we want to have some methodology to predict failure if you were to go into the cross tie itself and start changing loading applications, materials input, process parameters. We want to have a correlation between the final failure of the structure with something going on with the cross tie itself, whether it's a use case or whether it's a manufacturing case. So we have to start from the very fundamentals, the most basic. We begin with individual constituent properties, the properties of polypropylene, properties of polyethylene, of the fiberglass, of the foaming agent, and we go through a series of tests on this, whether it's structural tests, whether it's chemical tests, whether it's thermal tests, to build up this database of these material properties. These are our inputs for our modeling. Now, the reason we have to have this huge materials database is we have a whole host of these recycled materials that are in here. It's not consistent blends. There's a lot of variation batch to batch. And so we have to include all of that variability within the modeling itself. Again, we're working from base material properties to build a macroscopic model. This is also a geometry that is a celled composite. This is a foamed object that causes this densified outer shell, which enhances the structural performance, at the same time keeping it lightweight. But those cells have to be accounted for in the modeling behavior. So one of the things I'm indicating here is we're taking individual slices of the individual cells, the full three-dimensional cell variation, and building that into a more macro model where you end up having a smooth, not a homogenized material, but a continuous gradient of the cell properties throughout here. So that's built into the modeling as well. Then once we have the model fully built from the individual properties up to the macro, we can start looking at the loading conditions, whether it's dynamic loading, such as seen as you go across but you're essentially, as you're going across each individual cross tie, or we can start looking at an impact scenario. So it turns out this is a viscoelastic material, but when you hit it and impact it, there is a large amount of recovery that we can get. And so building all of that into a more unified framework. So what has to go into this? There's a lot of pieces of this. Piece number one, we have fibers, we have a matrix. These fibers and matrix, we're putting them together to build up this macro model of properties. So this is a micromechanics model that builds from the individual properties of the two, looking at variations of aspect ratio, variations of volume fraction, and build a macro model of this structure, of this micro scale variations. But these are all perfectly aligned fibers, not relevant to the scenario we're in. What we're dealing with is a scenario where things are chaotic and rolling and tumbling, and they have some preferential alignment, but they don't have this perfectly aligned scenario, much like you get, say, in an aerospace unidirectional composite. This is more like an injection molded style, where you have spatial variations in the orientation. So we have to do this orientation homogenization, where we're going to take the unidirectional properties and blend it through this homogenization to give you the homogenized material properties. And now that's from a structural stiffness perspective, but now we need the structural strength perspective. And we're using a modified rule of mixtures to build into this one. So the stiffness and these reference stresses of the foamed materials, once we have the modified rule of mixtures, we then look at the foamed material system. Once we have the foamed material system, then we can feed all of those individual pieces into a macro finite model to look at how the whole thing behaves. So let's peel off a couple of these pieces. First piece is, where do we get the individual properties from? So we have tensile bars that we can fabricate of polyethylene. We can do structural tests on that. We can do thermal tests, and now we have the properties of polyethylene. But combined with this is we have a blend with a polypropylene as well. It's an 88% to 12% blend of these materials. That's just sort of the nature of the feedstock of these recycled materials that for this particular example. So this particular polyethylene blend, we then blend these two properties together to give you sort of this rule of mixtures form of the matrix properties. We then need the fiberglass properties as well. And those are taken from the literature for fiberglass samples. These are e-glass fibers. So these are all of our inputs into the micromechanic model. Matrix fiber properties are now individually, we can tune them. So if we change our blend, if we change our packing density, if we change the aspect ratio, we change the orientation, these are now input parameters for the model that we can now vary as we go. We then take all of this and feed this into the Tan and Wang model to predict essentially the unidirectional stiffness locally. This is a spatially varying property, but this is the unidirectional. And again, what you see here, so this is different than, say, for a standard isotropic material. Isotropic material, you'd have two constants in this equation. You don't have two constants. We have here, for this particular one, we have 5 material constants that we end up needing. But those 5 material constants come from the constitutive properties of the polymer and the fiber. But again, this is now unidirectional. Our next thing we need to do is we need to homogenize based on the orientation. So what I mean by that is these fibers are all misaligned in different directions. So we need to look at that misalignment and include that all into our construct. So where that boils down into is each fiber is pointed along this vector P. We take each one and the next one and the next one and the next one and the next one and sum those up. Or if you think in terms of integrations, a summation and integration are the same thing, they're interchangeable. So we're going to sum the probability psi of the fiber pointing along certain axes over the entire unit sphere. And we end up getting a tensor. So we've taken a continuous function, psi, and written it as a tensor function. So now instead of having a smooth continuous function we have to keep track of, we now only have to keep track of either 5 orientation constants, or in terms of 4th order tensor, we only have to look at 15 orientation constants, much smaller than a smooth continuous function. Now that we know the orientation of the fibers within the system, we can then look at it. In this case, this is for a perfectly random scenario, so 1/3 along the diagonals. That is a perfectly random distribution, but if it was perfectly aligned, it would have 1 on one of the diagonal components and 0 in other places. Sometimes it's aligned off axis, so you end up having a point A and a point 2, and then something off axis, that's like point 1. But this can encompass the orientation. Now that we have an orientation state, we feed it into the stiffness homogenization. That stiffness homogenization has built into it each of the material constants from a unidirectional stiffness set. So those B1s, B2s, B3s, those are all from that previous slide's unidirectional stiffness, but now it's homogenized over orientation space. So now I can give you a monoclinic stiffness tensor representative of these misaligned fibers. Once we have that, we often in engineering like to relate it back to material constants. We often think in terms of like Young's modulus, Poisson's ratio. For example, one of those constants, E11, EII in this case, but say for example, I want the Young's modulus along the one axis, I need the 1 over the 1 component of the compliance tensor being the inverse of the stiff. We can get there. We go from stiffness to compliance to the material property that we're used to reporting in the literature. It takes a little bit of work, but it's all fully contained within that CIJKL term. So if you want to pull off the Poisson's ratio on the one face and the two direction, that's buried inside of those components of the CIJKL or that stiffness tensor. So we've gone from basic properties of polymer fiber to homogenize those for variations in fiber orientation. And now we have stiffness components that we can now compare to what we make in the structural testing machine. So we do a structural test. We pull the sample, we load it, and we can measure the Young's modulus and go, hey, this aligns with what we predicted experimentally. And we've done that. We actually have a couple papers out there in literature that talk about this one. So we validated the model from the stiffness perspective. And we also have the model, and I'm showing here, is we've validated off of now the failure aspect. So what I mean by failure is now we're doing this modified rule of mixtures where I have an orientation aspect to it, coupled with a length distribution aspect to it, looking at the critical length of the fiber to get optimal strength performance out of this. And you can essentially predict the composite failure stress. That's what that sigma C is. So we build in the matrix property, sigma M, with the fiber property, sigma F. Poisson's ratios, that's that new F and the new M that's buried inside of there. Oh, I'm sorry, that's the volume fraction inside there. We blend those together using the modified rule of mixtures, and out comes the composite failure stiffness or failure strength. And that's what we end up getting right here on this model. So you can actually see that our stress, where we predict it to occur, that's where the cross hatch occurs, is also the exact same location as where the model says that offset would occur. So we validate then the strength prediction. Now that we have the strength prediction, we now go one level of refinement further, and now we're talking about the foam itself. Building into the foam, spatial variations in the foam, so you can see that this is not a uniformly homogenized structure, but we can work that through the model. And we used, again, a power law relationship for this one. And again, we can talk about the foam stress properties from the composite, the fully densified properties. So we can now go from each individual component, building it up to the full structure that we're looking at. So with that, let me hand it back over to Daniel.
For the model validation, there's this 4-point bend test that we do for over 16 different cross ties. There's 2 points of reaction, there's 2 points of loading, and you see the positive and then it breaks. So once it breaks, you have your stress and your displacement. And this will be used to verify with the FEA model, the finite element analysis model, and show are we within the ballpark of what we're seeing that is in the experimental tests, or how close are we to do that? This is the 16 different tests that we saw, and that the black line you see is the average of all the 16 different tests. This is a 10-year Solson machine, which is capable of loading 120,000 pounds, and within the 16 different tests, we have seen 3.58 kilonewton experimental variation between one sample to the other, over 100,000 kilonewton, 100,000 newtons. That is not a huge experimental variation. So with all these predicted shell material properties and the core material properties, the tensile modulus, the reference stress for a given reference strain, this is the curve that we've gotten from the finite element analysis model. So this E is what's being entered into the Romberg-Osgood model, as well as the sigma ref, which is predicted, as David mentioned earlier. And so that is a simulated 4-point bend testing. And so we have overall validated that the 4-point bend test from the experimental results and the finite element results are almost identical for all validation purposes. Now we have that information. We can take it into a real world situation and see how that works. Are we able to compare it to a moving train on a track? And so there's multiple layers within the rail track. So you have the wheel, and there's the rail, and which is situated on the crosstie. The crossties are over a ballast, and each of these have to be modeled to get an in situ loading condition. So all the foundation can be taken as a spring constant and can be applied under the finite element analysis model. You have two loading conditions as a 4-point bend test, but here it is the width of the rail track. And so once you have that, you run a simulation, and the spring constant is taken as 33 Newton millimeter square, and there's a damping constant that can also be taken. This is all from literature that has been used as the material constants for the spring foundation. And a cyclic loading is applied to get a continuous dynamic loading condition. So on the left, you see that there is a real track that is, a train is going on it, and then you can see the movement of the cross ties. And on the right, you see the loading in a finite element analysis model. It is very obvious that you can see these the cross ties moving along with this, and we've shown how that we can compare the actual results in the in situ testing conditions and compare that to the finite element analysis models. Further, like David mentioned, the cross ties being polymers, they have a viscoelastic behavior. We wanted a study of how much, if you impact the cross tie, will there be recovery within, say, 30 to 50 days. So we have created a drop weight impact tester. You can see that there's an impactor which is hitting the surface of the cross tie, and notice this changing shape, that you can see that this kink in the graph is showing a viscoelastic behavior. And once you have that, there's a crater that is forming, showing where the actual impact happened. We can take this and put it into two different environmental chambers. One is loaded at 20 degrees centigrade and another one at 60 degrees. We want to study how quickly there is a recovery based on the temperature profile that we're studying. So after a minute of the test, it was put under a microscope, which is a 3D microscope, and you can level it out and see, based on every 5 minutes to 15 minutes, how much depth recovery has taken place. So these 3 points are selected and the depth is measured, and we've done that for over 50 days, and you can see that there is a slower recovery happening for the 20 degrees C, whereas 60 degrees C has recovered fast and has stabilized comparatively sooner than, as you can see, in the 20 degrees C samples. So overall, yeah, we have talked about the mathematical modeling, the finite elements analysis, 4-point bend testing. We've done a lot of model validation, and we have even applied what we have analyzed into in situ loading problem, and we've even considered looking at the recovery and the viscoelastic behavior of the composite railroad cross tie. So yeah, overall, this is what we have done, and we are continuously working on this to look at further viscoelastic properties. And yeah, thank you so much for your time.